Hello and welcome to the third Physics 2211 lab, Black Hole. This lab is broken into three parts. The purpose of part one is to find the mass of the black hole. The purpose of part two is to use the mass of the black hole to find the initial velocity of the ship so that we can ensure that there are no collisions of the ship with the black hole. Part three, or the what if question, is to find the initial velocity of the ship to ensure an orbit around the black hole. Fundamental principles we need are Newton's second law of motion, the momentum principle, which is that the net force is equal to mass times acceleration, and the force of gravity. As a preview to the results of this lab, the mass of the black hole is 1.1 times 10 to the 34 kilograms, and the initial velocity of the ship is minus 6.13 times 10 to the 6th in the x direction, 8.41 times 10 to the 6th in the y direction, and 0 in the z. We've also got the universal law of gravitation. F sub g is equal to the gravitational constant times m1 times m2, all divided by r squared times negative r hat, and the magnitude of F sub g. We also have Newton's second law, or the momentum principle, which is F net is equal to the change in momentum over the change in time. In addition, F net can be broken into its two components, the parallel and perpendicular component, as well as the velocity update and the position update formulas as we've seen before. In this lab, we're going to assume that the net force is equal to the gravitational force. And that is because we are in space. So we are assuming that the only force acting on these objects is the force of gravity from the other objects given in the prompt of this lab. Since universal gravitation is a non-constant force, we will let average velocity be approximately equal to the final velocity. We also just can't find the average velocity for this. We also know that changes in the parallel force will change the magnitude of the force, and changes in perpendicular force will change the direction of the force. Okay, so in part one, we will assign our system to be the star and our surroundings to be the black hole. Our gravitational constant g is always the same. The mass of our star is 2 times 10 to the 30th, and our delta t is the time of 1 day converted into seconds. We're also starting at t equals 0. All right, so let's look at our code. In the block on the left, we are calculating the net force on our little star due to the black hole. And on the right, we're calculating our parallel and perpendicular components of the net force. At the bottom, we're using our net force to calculate the mass of the black hole. And here's our results. We found our F net, which is 7.97 times 10 to the 28th. Our F net parallel is 1.4 times 10 to the 28th. Our F net perpendicular is 7.8 times 10 to the 28th, and the mass of our black hole is 1.1 times 10 to the 34. All right, in part two, we're going to assign our system as the spaceship and our surroundings, which is the planet and black hole. Our initial conditions in part two are largely the same. We've got our gravitational constant, big G, the mass of our planet, 9 times 10 to the 28th, the mass of the ship, 7 times 10 to the 10th, and our delta t, 1 second. We're using the exact same mass of the black hole that we calculated in the last part in this part as well. And our initial conditions for the planet are given in the source code. All right, so our first step is to calculate our net force acting on our planet and then the net force acting on our ship. To do this, we've got to find the force acting on the planet due to the black hole and the force due to the ship. Adding them together gives F net on the planet, and we do the same thing for the ship. All right, and then we've got our velocity and position update formulas that we use to predict the motion of our planet as well as our ship. As you can see here, here's the graph. We calculated that with a speed of negative 6.16 times 10 to the 6th in the x direction and 8.141 times 10 to the 6th in the y direction, we were able to escape the black hole. So a possible source of error in part one is that we could have had our program run for a little longer to calculate a more accurate average mass of the black hole. In part two, I initially guessed and checked a lot to find the initial velocity, so it might not have been the most optimal one. The time interval also might have been too short. Maybe later on the ship will circle back and hit the black hole. We're not too sure because I didn't run it for that long. All right, so what does it mean question asks for the difference between the parallel and perpendicular components of the net force and the parallel and perpendicular components of the rate of change in momentum. And these two things are the exact same because the rate of change in momentum is just the net force given by the momentum principle. It's a lot easier to find the change in momentum than it is to find the net force, which is why we've done this in all our labs. So the what if question is asking what the initial conditions for the ship's speed are for the ship to be able to orbit around the black hole. And we found that negative 6.13 times 10 to the 6th in the x direction and 8.41 times 10 to the 6th in the y direction is the perfect initial velocity for the ship to orbit the black hole. As you can see on the left, we've got a snapshot in time, and at the end, we show the full thing. All right, that's it for today. Thanks for watching.